So Phil laid out the problem well and shows why solar EUV is important. I'm Rodney Varick. I'm from the Space Weather Prediction Center. I bring a slightly different slant because we are an operational space weather center, so we're looking more at turning all of the science into something operational. So I'm going to talk a little bit about real-time running of models, and that's going to be an important factor. I'll talk about the EUV proxies. I'm going to shift gear a little bit and talk about F10 and sunspot number, and then a magnesium core to wing, sort of show how they work, where the proxies work, and where they fail. Phil started this off. Already went through the first two bullets. I'll skip them. But measuring solar EUV irradiance is very difficult. It's got to be done from space. It's difficult to obtain sensor stability over many years, and this has been a problem and continues to be a challenge, and often requires rocket underflights or some other form of cross-calibration to maintain that stability. We often represent irradiance over the long time periods with proxies. This is the solar spectrum. This is now at a quarter nanometer or quarter angstrom resolution, and actually this is way too much information. In fact, you can see that there are thousands of spectral lines in there, and if you really wanted to capture the entire subtle inputs of the sun into the thermosphere-ionosphere system, you should keep track of all those. This is an NRL model with Harry Warren and Judith Lean. The thing I want to point out here is that this difference between solar min and solar max and solar flares, out at these long wavelengths, you can see there's a little bit of a difference, but it's quite small. When you get to the shorter wavelengths, you get much larger variability during solar min, solar max, and solar flares. The other thing that happens is that all of these lines, a lot of them come up only during the solar flare itself. This is now the same spectrum, only at a lower resolution and going out a little further, so I've got Lyman alpha in here showing the same information, solar min, solar max, and solar flare. And down here I've plotted the ratio, so you can see what magnitude of variability over here. So at these very short wavelengths, you have a factor of 10 change, or even a factor of 100 when you get down to the X-ray wavelengths. And that's the strong variability at the very short wavelengths. You still have quite a bit of variability in the below 40 nanometers, as Phil points out, that's where the photoelectrons are all being produced. And as you get to longer and longer wavelengths, Lyman alpha, which is the brightest line in this spectral region, in fact, it carries more energy in that one spectral line than the entire solar wind, but it doesn't vary very much. So it's a much stabler spectral emission. So then, as Phil said, you combine this solar spectrum with all the cross sections of N2, O2, and O, and you can see here that the cross sections fall off at the short wavelengths and at the long wavelengths, but here in the middle, the cross sections are the largest. And so you combine that information with the atmospheric density, and you can get a measure of where in the atmosphere the solar EUV irradiance deposits its energy. So this is now, the color plot is now wavelength and altitude. And you can see the solar spectrum here in white. One of the lines here is this 304 line, and I'm going to talk about that because A, it's very bright, carries a lot of the energy. B, it's in this important part of the spectrum, and it has a lot of variability with solar, during the solar variability phase. I think I've got that one. There are a number of models. I just list them here. I'm not going to go into them or anything, but each of these over time has tried to come up with ways to model the solar EUV spectrum in a way that's compatible with thermosphere-ionosphere models. You can't take thousands of spectral lines and then incorporate them into a model at every time step, at every spatial resolution. It's just way too much information. So trying to parameterize this and drive it with whatever proxies available during this period, there weren't measurements available. F10 became the primary driver for most of these models. So now we're going to switch gears from spectra to time series. In terms of EUV time series, there very few existed over the long periods. As I said, this is repeat, but there are no continuous EUV measurements that span more than a decade, more than a solar cycle. So proxies are required. And these are the proxies. I'll go through them quickly. Sunspot number you've all seen, F10.7, a very good proxy, goes back to 1947. The magnesium core to wing only goes back to 1978, but it turns out it's got some value. And then this is actually a measurement. This is one of the longest measurements of solar EUV irradiance from the SOHO satellite. This is the 304 line, measured at very high cadence, but I've shown daily measurements and then an 81-day smooth. And you can see the solar cycle. And I'm going to use this as Phil compared to AE. I'm going to compare to this particular time series here. So when you compare oops, I went too fast. Sunspot number to the 304 actual measurement, you see a lot of scatter. You also see that Sunspot stops at 0. There are no negative sunspot numbers. So you have a flattening at the bottom. I would recommend, even though IRI still uses sunspot number, although it's been parameterized to use F10, don't use sunspot number. It's really not a very good proxy for EUV. Now this is F10, and Phil showed that it works very well. This is not including any kind of 81-day average. This is just the F10. Now this is the same plot that Phil showed, only now I'm comparing with the SOHO data. But again, you start to see here, just like sunspot number, F10 actually starts to level off as well at the very low values. And this will show up to be a problem in a minute. This is now the magnesium. This is one that I work on, so I'm taking this opportunity to advertise what I work on. This actually works very well. It doesn't flatten out at the bottom. It's a little tighter, a little higher correlation coefficient. But again, there's quite a bit of scatter. And if we start looking at the actual time series themselves, so this is a few month period in 2002, and you can see the solar cycle modulation. The blue is the data that we want to compare with, and all these others are the proxies. Pink is the sunspot number. And I'll just say right now, it does not track well. There are huge variabilities that are not associated with the actual EUV flux, so don't use sunspot number if you can avoid it. The other ones do a little bit better. I'm going to blow up now. I'm going to just stop talking about sunspot number. Now this is just F10 and the magnesium. So if you scale a solar cycle's worth of information and then look at how it does in a short region, you can see the solar rotation modulation. This is a 27-day modulation, but obviously both of these proxies overestimate that solar rotation modulation. That's one of the reasons why when you add a 27 or an 81-day smoothed component, so you now take F10 plus its 81-day smooth, you can really reduce that scatter. Now the correlation coefficients go up quite high, 0.97 or 0.98 for magnesium, and you can see that the scatter is reduced. Now, the problem from my perspective is this introduces a very serious limitation. You can't run it in real time with an 81-day average. You have to come up with some other parameterization to be able to run in real time. You can't wait for 41 days for the full 81-day smooth. So this is a problem. It's been worked around in some cases, but you're not going to get that kind of correlation with a different formulation. But obviously now when you fit it, you can see that we've reduced a lot of scatter and we've actually captured the solar rotation modulation quite well. But we've introduced another issue, which is now we start seeing offsets. And you can see some here, especially at solar minimum, and you can see here on this declining phase that F10 in this period was high. I can find other examples where magnesium is different. At this point, I can't tell you which is the most accurate because the data itself also has some probable issues because I know for a fact that they have a strong degradation over this 14-year data set, and they've had to remove it. So I can't tell you which of these is the most accurate representation of the solar EUV flux. But now let's take a look. I'm going to shift gears a little bit and look at some of the long-term trends and try and identify which of those the data or the proxy does the best. And the data I'm going to be using is a 400-kilometer density. This is from John Emmert at NRL, based on satellite drag information. So it's a really, really good data set. Obviously, you see the solar cycle variability. The daily are in gray. No, actually, a 4-day running average in gray and then a yearly average in red. So I'm going to try and reproduce this using those solar proxies. One of the things I've done, which kind of cheats, is to plot this on a log scale to highlight the solar minima. And you can see a general downward trend. The assumption here is that these three are down. The downward trend is associated with the anthropogenic forcing in the lower atmosphere, the redistribution of energy. You know, at the ground it heats up. In the middle atmosphere you get a cooling. That cooling in the middle atmosphere actually brings the whole atmosphere down, which then causes a reduction in the density at 400 kilometers. But then this last drop is quite large. This was where I think the density dropped by 40%, and then when the news, NASA puts out press releases saying that the sky is falling, that the space is now 40 kilometers closer than it used to be, things like that. But it is a very remarkable drop, and it's been a challenge to try and identify what are the causes of that very significant drop in neutral density at this altitude. If you look at that 304, the actual measurements of EUV flux, it too has a very large drop, in this case 18%. Now the question, is that real? Again, I told you that there's a lot of issues associated with long-term irradiance measurements. Now I'm going to use the EMSIS model. Again, it's an empirical model, And I've scaled the magnesium and the SEM measurements to F10 so that I can just run the model as is. And you see a couple of things. First of all, I've removed a CO2 component. So basically, I fit a CO2 curve to these three minima and then just assumed that it was going to follow that same trend out here. It still it did not account for this large drop. The other thing you notice is a remarkable agreement. For 30 years, AMSIS reproduces the satellite drag 400 kilometer density extremely well. You can't even see the lines on top of each other. But then here at the end of this time series, things start to diverge and the agreement falls apart. And on the next one, I'm just blowing up the bottom part, and you can see that, as I mentioned earlier, F10.7 tends to bottom out. It tends to go level. And in fact here, I guess that that's what's happened. It is not representing that solar minimum because it's reached some sort of minimum that's not associated with, not correlated with the EUV flux. Now this may become more and more of an issue because, as we know, this recent sunspot cycle is small, and we anticipate that it'll probably continue to be low, so the solar minima values may be changing to the point where F10 is no longer going to capture the true irradiance at those low values. On the other hand, the true measurement, the 304, went way too far. It overestimated this reduction. The magnesium seems to have done quite well. So if you use accept all the assumptions and qualifiers that I used to create this, then you can say that the magnesium is capturing long-term trend information very well. So in terms of I'm almost done here. In terms of the EUV proxies, Sunspot number, unless you want to go look at what happened at the Maunder minimum, and I wouldn't even hazard a guess as to whether sunspots can represent EUV flux back that far. I wouldn't even use it. F10 is a very good proxy, but it may start to level off at solar minimum. We may see this as more and more of a problem. The magnesium core to wing is a very good proxy. It extends back 3 cycles. I think it will be useful even into the future as a way to help bound some of the EUV measurements. And Frank will talk about this in a minute. Now, unfortunately, there are some caveats. First of all, the inclusion of an 81-day smooth component really precludes it from being used in operations where you want to run a value today and get a forecast for tomorrow. None of these proxies will work for anything shorter than a day. They're daily averages. So if you want to look at the solar flares, you've got to use actual EUV measurements. And I think we're entering a new era of EUV observations. We've got improved accuracy. The SOHO measurement started in 1996. The sensor was built in the late 80s and early 90s. So the technology is really 30 years old. So now we are in a new era. These sensors are more stable, the calibrations are better, and we've got lots of them. And that, as Phil mentioned, it's time to use EUV irradiances to drive the models as inputs into the thermosphere-ionosphere system. Ooh, what happened there? Oh, that didn't work. Butterfinger, sorry about that. And this just shows, since solar minimum, since 2010, we have a number of measurements of 304, and they're all capturing all the salient features of the EUV irradiance, and there are all sorts of other wavelengths in there. Now the other thing is solar flares. This is just an example of 2 flares, an X-class flare and an M-class flare. So in the X-rays, there's an order of magnitude difference in the flux. But if you look at Lyman alpha, they have exactly the same magnitude change. If you look at 304, the big flare is a 45% change, the small flare 20%, so now you've got a factor of 2 difference. And if you go to the shorter wavelengths, you're going from 80% to 600%, so you almost have your order of magnitude change. So you need a lot of spectral information to study flares, and in addition, you can see that there's 2 components. There's a prompt component and a gradual component to the flare, and in some cases it's large, and in other cases you can hardly see it. So the time history of a flare is also very complicated. There are all kinds of other issues associated with flares and with solar spectral irradiance in terms of solar atmospheric absorption and things like that really require fairly complex measurements in order to capture it all. Anyway, I'm not going to read through the summary. I will leave it at that.